Okay, we are looking at Chapter 23, the one sample t-tests. And then on the next one, we'll do the interval. I apologize for the dark picture. A company with a large fleet of cars hopes to keep gasoline costs down and sets a goal of attaining a fleet average of at least 26 miles per gallon. To see if the goal is being met, they check the gasoline usage for 50 company trips chosen at random, finding a mean of 25.02 and a standard deviation of 4.83. Is this strong evidence that they have failed to attain their fuel economy goal? So we have the mean that they'd like to reach is 26. Their goal is to be 26 or more, and our question is, are they failing that? So our hypothesis is that mu is equal to 26, and our alternative is that it's less than 26, because that would mean they failed to meet that goal of being 26 or over. Our sample mean, x bar, is 25.02, and our standard deviation is 4.83. It tells us the 50 cars, so n is 50, are chosen at random. So we're going to check our conditions now. Alpha is 0.05. All right, so now let's check our conditions. The first one is that 50 is less than 10% of all cars, of all trips taken. And the second one is the sample was random. And this is actually a random sample. It's important you are very specific with this. If it's not a random sample, you need to say representative. If it's an experiment, you need to say randomize or random assignment to the treatment groups. You get marked off for not being specific here. So the sample is random. And then we don't have the data, so we can't look at a histogram, but we can say that 50 is large enough to apply the central limit theorem. And that number is 30. Okay, it has to be greater than 30, and then the central limit theorem applies. The central limit theorem says if our sample is large enough, then even if the population is skewed, the sampling distribution will be normal. And that's what this condition is checking. Will the sampling distribution for the mean be normal? So since conditions are met, a normal model is, or a T model is appropriate. And I will use a one sample t-test. And we're going to state our degrees of freedom with degrees of freedom is n minus 1. So 50 minus 1 is 49 degrees of freedom. And then we can perform our test. Our t-score is our sample mean, 25.02, minus the hypothesized mean, 26, divided by the standard deviation over the square root of 50. If you ever have a sample size, your standard deviation must be divided by the square root of the sample size. And so that is negative 0.98 divided by 0.683. Negative 0.98 divided by the answer, and that's negative 1.435. And then we're going to do TCDF, negative 99, because our alternative hypothesis is less than, negative 1.435, comma, degrees of freedom, 49. This gives us our p-value. So it's second distribution, TCDF, 49 degrees of freedom. P-value is 0.079. So, I mean, p-value is 0.079. Our mu is 26, that's our h naught, and our x bar was 25.02. So that means I'm going to type this. Since my p-value of 0.079 is greater than my alpha of 0.05, I fail to reject the null hypothesis. There is not enough evidence to convince me the true mean gas mileage is not 26 miles per gallon. And interpreter p-value is if the true mean gas mileage of the cars is 26, there is a 0.079 chance of obtaining our sample mean of 25.02 miles per gallon. Let me make this all bigger. Select all. Make it a little bigger for you guys to see. Okay, so that's your conclusion. The conclusion is since my p-value of 0.079 is greater than my alpha 0.05, I fail to reject the null hypothesis. There's not enough evidence. When we reject, there's not enough when we fail to reject, it's because we don't think that it's actually different. Our sample difference from the mean could just be from sampling variation. So we don't think that it's different from the 26 miles per gallon goal. And that probability of getting that sample of 25.02 if the true gas mileage was 26 is our p-value. That's what the p-value means. Okay, so some students checked 6 bags of Doritos marked with a net weight of 28.3 grams. They carefully weighed the contents of each bag, recording the following weights. Do they satisfy assumptions for inference? Find the mean and standard deviation of the weights, and then create a 95% confidence interval. So when we are given a list of data, okay, we have to go to our calculator. And let's see. We have to go to our calculator, and it's stat, right? Edit, and you're going to put the data into list 1. Okay. After you have the data in list 1, you're going to go back and hit stat, calc, var stats, and my list 1, and then calculate. And then we're going to write this down, x bar. We're going to write this down, x bar equals 28.98, and s equals 0.36. So we're getting this information. That's our mean and our standard deviation. Now that I have that, let's see. Let's move this out of the way. I'm going to check my conditions. 6 is less than 10% of all bags of Doritos. I don't think the sample was random. It just says they checked 6 bags. But this is one of those cases where we can assume it's representative because there's nothing special about where the bags go, right? So the sample is representative. And the last one is nearly normal. Now our sample size is definitely not large enough to say we can use the central limit theorem, which requires 30 or more. So we need to go back to the calculator. Okay. I think I have to add another video. And look at the data. So I'm going to do this on another page. So we need to go back here and we need to look at our data. We're going to go to the stat plot. I'm going to go over to my normal probability plot, because my guess is with 6 values, a histogram's not going to be nearly normal. And then I'm going to go list 1. Oops. Second L1. And then zoom 9. And that's not so bad, right? So our nearly normal condition is that the normal probability plot is straight enough. And we really need to just draw what we see.
And it doesn't matter if it's under 30?
No, if it's under 30 and the normal probability plot is straight enough, then the conditions are met. Okay, so since conditions are met, a T model is appropriate, and I will use a one sample T interval. This one asked for the interval, right? With, I had 6 minus 1 is 5 degrees of freedom. You don't need to write the 6 minus 1, but I just put that there so you know where I got it. So their sample size was 6, the degrees of freedom is 6 minus 1. And then so my interval is my sample x bar plus or minus t star with degrees of freedom, and then s over the square root of n. So my x bar was 28.9. 28.983, oops, I don't need to write that, plus or minus, and I need to find my degrees of freedom from my table. So I'm going to find my table, and 95% confident with 6 degrees of freedom should be 2.447. So that's 2.447 from the table. And then S was 0.36, so 0.36 over the square root of 6. Okay, and then I do that in my calculator. I get 28.623 to 29.34. 342. And so I am 95% confident. The true mean weight of a bag of Doritos is between 28.623 and 29.342 grams. Okay, and then the last question asks, well, the bag says 28.3. What do we think about that? So since 28.3 is actually below our interval, we actually believe they give you more chips than is stated. Okay, so we believe that it is greater than that because 28.63 is below my interval. If it was above our interval, then we would say we believe it's less than that. If it's in our interval, we believe it's about the same.